Welcome to the fourth day of Summer General Physics. In this third video, we'll be looking at centripetal acceleration. So centripetal acceleration is the kind of acceleration you get because an object is moving in a circle. If you think about an object moving in a circle, even if it's at constant speed, it will still have acceleration because the direction of its velocity vector is changing. So in this picture here, we have a little cartoon of a car going around a circular racetrack. And let's say the speed of the car is constant. It's always going 30 miles an hour. But you can see that the direction of the velocity vector is changing, and because of the change in direction, we will have an acceleration. We know that the average acceleration of an object is its final velocity minus its initial velocity over the change in time. So this implies that the direction of the acceleration will be equal to the direction of the difference between the two velocity vectors. So let's consider these two velocity vectors that are taken a close time apart. And if we want to find the average acceleration, we would take the final velocity vector and subtract the initial velocity vector from it. So let's redraw our velocity vectors over here. So this is the final velocity vector. Then if we subtract the initial velocity vector, that means we take the negative, or flip the direction, and add it to the final velocity vector. So the sum of those becomes the acceleration, or actually the acceleration times the time interval. But this shows us the direction of the acceleration vector. And as you can see, the direction of the acceleration vector, and if we're doing an average, it should be taken from about here, is pointing towards the center of the circle. And in fact, that would be true no matter where you are on the circular racetrack. At every point on the circular racetrack, since the velocity vector is changing direction, there is an acceleration, and that acceleration points towards the center of the circle. So we typically write the centripetal acceleration with a subscript a sub c, and that centripetal acceleration always points towards the center of the circle. And it always has the same magnitude, or the same equation for calculating its magnitude. So the direction of the centripetal acceleration is towards the center of rotation, and it has a magnitude of the speed squared divided by r, where r is the radius of the circle that the object is traveling around. So that means if you have an object that is going in a circle, there are two possible kinds of acceleration. If the object is moving, you're going to have centripetal acceleration from moving in a circle, and that is due to the change in direction of the velocity vector. And then you can also have tangential acceleration, which is tangent to the circular path, and the tangential acceleration is responsible for speeding up the object or slowing it down. So if the rotation is speeding up or slowing down, if there's a change in speed, then there will be a tangential acceleration. If there is motion in a circle, there will always be a centripetal acceleration. Then if you need to find the total or net acceleration, since these two vectors are always perpendicular to each other, you can use the Pythagorean theorem in order to find the vector sum, or the magnitude of that vector sum. So here is a question for you. Let's say there is an object which is moving in a circular path with a constant speed. Which of the following is true concerning this object? Is its velocity constant, but its acceleration changing? Is its acceleration constant but velocity changing? Are both the acceleration and velocity changing, or are they constant? So pause the video here and think over these different choices and pick the one that you think is correct. Okay, so now that you've had a chance to think over these different options, which of the following would be true concerning this object? Well, we know that the speed is constant, but is the velocity changing? Well, if the object is moving in a circle, then the direction of the velocity vector is changing, So since velocity is a vector, the velocity is technically changing. The magnitude of the velocity is not changing, but its direction is. So the velocity vector is changing. What about the acceleration? There's no tangential acceleration in this case, but there would be centripetal acceleration. The centripetal acceleration magnitude is constant, since the equation for centripetal acceleration is v squared over r, and v is constant and r is constant. So the magnitude of the centripetal acceleration is constant, but since the centripetal acceleration vector always points towards the center of the circle, the direction towards the center of the circle is always changing for an object going in a circle. So that means both the acceleration and the velocity are changing, not their magnitudes, but their directions are. So I would choose option C for this question. So finally, let's look at an example that has to do with centripetal acceleration. So in this example, a race car is starting from rest, and it's on a circular track of radius 400 meters. The car's speed increases at a constant rate of 0.5 meters per second squared. So at the point where the centripetal and tangential accelerations are equal, we need to figure out the speed of the race car, the distance it has traveled to get to this point, and the elapsed time. All right, so let's first draw a picture of this problem. So we have a car that's moving around a circular racetrack. So here is our racetrack, and here's the car that's moving around the circular racetrack. And the racetrack has a radius, and I'll call that radius r, and r is 400 meters. The car's speed is increasing at a constant rate of 0.5 meters per second squared. So that's how fast the car's speed is increasing. That tells us how the car is speeding up. So an acceleration that causes a speeding up is a tangential acceleration. And this sounds like a tangential acceleration to me. It's causing the car to go faster. Centripetal accelerations don't cause something to speed up or slow down. They just cause a change in direction. So this would be the tangential acceleration that has a value of 0.5 meters per second squared. We want to know something about the point where the magnitudes of the centripetal and tangential accelerations are equal. So we want to know something about where the tangential acceleration is equal to the centripetal acceleration. All right, so how do we go about solving this problem? Well, I already have a value for the tangential acceleration. And I know that at the point I'm interested in, the tangential acceleration is equal to the centripetal acceleration. One other thing I know is that centripetal acceleration is always, always, always equal to v squared over r, where v is the speed. So let's see. I know that tangential acceleration is v squared over r. I know what my r is. I know what tangential acceleration is. So that means I should be able to find what v is. I should be able to find the speed, which would be the answer to part A of my question. So let me rewrite this. Tangential acceleration is equal to centripetal, but that's equal to v squared over r. So if I'm solving for v, I can multiply both sides by r. And then I would take the square root of both sides. So that means the speed of the car would be the square root of r times the tangential acceleration. And plugging in numbers, r is 400 meters. And the tangential acceleration at this point is 0.5 meters per second squared. So that gives me a speed at that point on the racetrack of 14.1 meters per second. All right, so that looks like my answer to part A of the question. So part B is asking, how far did the car travel, going from rest to 14.1 meters per second? This sounds to me like it might be a constant acceleration type problem. So I should write down a list of the things that I know. So what are my knowns? Well, one thing I know is that the car started at rest. So the initial velocity is 0, and I know the final velocity because I'm interested in how far the car went from when it was at rest to when it achieved this final velocity. So that would be 14.1 meters per second. Anything else that I know? I know the acceleration. The acceleration that was causing the speeding up. So the acceleration that was causing the speeding up was my tangential acceleration. And so that was 0.5 meters per second squared. I think that's it for things I know at this point. And the unknown I want to find is distance traveled, or displacement. And I'll call that delta x. It's okay that in this case, delta x is kind of wrapped around the racetrack. So you should think of delta x, since the motion is going around the racetrack, you should think of delta x as being wrapped around the racetrack. And we will think of delta x as the displacement in that path along the racetrack. All right, so I have my list of knowns and my unknown. So then I should take a look at my constant acceleration equations and find one that will allow me to find delta x given my initial and final velocity and the acceleration that's causing the speeding up. And if I look at those equations, one that looks like it has promise is that delta x is equal to the final velocity squared minus the initial velocity squared divided by 2a. In fact, it already looks like it's solved for my unknown, so I can just plug in numbers. So the final velocity was 14.1 meters per second. I square that, minus the initial velocity was 0. 0 squared is just 0. And then I divide by 2 times the acceleration that's causing the speeding up, 0.5 meters per second squared. And that's going to give me a delta x of about 200 meters. So now I can add that 200 meters to my list of knowns. It's another thing I know about the problem. And that is my answer to part B. But then part C is asking for time. So now my new unknown is time. What is the elapsed time? So now I have all of these knowns, and I need to solve for time. There's a bunch of different equations that would work at this point because I have so many things that I've already solved for. But if I look at the constant acceleration equations, I think the one I'll choose is the one that says that final velocity is equal to initial velocity plus acceleration times time. I know that the initial velocity is 0, so that simplifies this equation greatly. Final velocity in this case would be just acceleration times time because the initial velocity is 0. And then I'm solving for time, so I can divide both sides by acceleration. So then the time, the elapsed time, would be the final velocity, 14.1 meters per second, divided by the acceleration, 0.5 meters per second squared. So I have an elapsed time of about 28.2 seconds. And that becomes my answer to part C of the problem. So you can see the strategy here. When I was thinking about centripetal acceleration, The acceleration that is due to the fact that the car is moving in a circle and its velocity vector is changing, that centripetal acceleration is always equal to v squared over r. The rest of the problem was really a constant acceleration problem, and I just needed to think about my displacement as being wrapped around the circle and use the acceleration that caused an increase in the velocity. So that concludes video 3. In the next video, we'll be considering relative motion.